Okay, guys, this is the walkthrough for Unit 6, Bellwork number 2. And you should probably notice that there's a whole lot of stuff on here that I've already asked you. So it's almost like, gee, Miss Goff, why are you bothering with that? But anyway, um, because normally we would have spaced this out a little bit more, but we're doing the best we can. Okay, so number 1, nebulas are basically large, clouds of gas and dust in space. We went over that in the first bell work. It's also in lesson 1. All right, so nebulas are basically large clouds of gas and dust. And there are 2 varieties of nebulas. Nebulas can be star-forming, meaning that the nebula collapses under its own gravity over time and forms stars. Star-forming nebulas are either emission, reflection, or dark nebulas. Nebulas can also form at the end of a star's life, and those would be star-ending or star-destroying. I mean, I kind of made that name up myself, but the type that are star-ending nebulas are your planetary nebulas and your supernova remnants. Okay, so planetary nebulas, remember, are formed when a star, similar to our sun, mass-wise, grows old, it swells, and it's going to shed its outer layers over time. And all that's left after that process is this big cloud of gas, which is the nebula, the planetary nebula. And usually there's a little white dwarf, which is the remains of the star, that is small and really dense at the center. So that's what they think is going to happen to the sun. Form a planetary nebula at the end of its life. If a star is more massive, then it will probably end its life in a more dramatic way using a supernova explosion. And the cloud that's left over at the end of a supernova explosion is called a supernova remnant. Remnant, remember, is just a word that means leftover. I go to the fabric store all the time, and there is always a section called remnants, like bits that are left over from, bolts that people didn't want. But anyway, a supernova remnant, it's the leftover from a supernova explosion. Typically after a supernova explosion, you've got the supernova remnant, which is the big cloud or nebula. And a lot of times you wind up having a neutron star, or sometimes called a pulsar, which is all that's left of the core, and it's super, super, super dense. Okay? All right, so that takes us through number 1, our description of nebulas again. What is the name for space that's completely empty? Completely empty space is also known as voids. Okay? And it's really important that you understand that, it's like really completely empty. There's no air, nothing. There's no molecules. It is a vacuum. Vacuum literally means like no air. Okay? So not even air. It's totally empty. And remember that completely empty space is what a lot of the universe is made of. There's a lot of just empty space in space. All right. Number 3. We are comparing the sun to other stars in the universe. So, we think our star is really great because it's our star. But in the grand scheme of things, our star is really average. Okay? So it's kind of like somebody saying, hey, your sun is just average. Okay? Your sun, our sun, the star in our solar system, is really kind of just an average sized star. It's about medium size, it's about medium temperature, it's not the biggest star, it's not the smallest star, it's not the hottest star, it's not the coolest star, and it ain't the brightest star either. And when I say it's not the brightest to us, which is apparent magnitude, but there are a lot of other stars out there that give off more light. So when I say it's not the brightest right here, I mean luminosity. I mean like how much light it's actually giving off. That would be absolute magnitude is what I'm talking about. Okay? All right. So our sun is so average. It's so average. All right. Number 4. Again, I can't stress this enough. How many stars are in our solar system? 1. It's the sun. It's the sun, and the rest of the solar system is planets and whatnot, all orbiting the sun. There's only one star in our solar system. Remember, there's billions of stars in the Milky Way galaxy. The sun is one of those billions. But in our solar system, there's only one, and that's the sun. Okay, next question. Why does the sun appear so much brighter than any of the other stars? Well, I just got finished telling you guys that our sun is average. It's not the brightest, it's not the dimmest, it's not the hottest, it's not the coolest. But the sun appears so much brighter to us because it is thousands and thousands and thousands times closer to us than any other star. So light from the sun takes a little over 8 minutes to reach us, traveling at the speed of light, because we are located about 150 million kilometers from the sun. The next closest star is 4.3 light years away, meaning traveling at the speed of light. Light from that star, which happens to be Proxima Centauri, light from that star takes 4.3 years to reach us. So you can see that our sun is way closer to us than any other star. Okay? All right. What makes its own light? A self-luminous celestial body. Self-luminous means something that makes its own light. Celestial body means just like a heavenly body, an object out in space. So what is a self-luminous celestial body made primarily of hydrogen gas? And it emits light and energy because of nuclear fusion. I am describing a star. Okay? In lesson 3, you're going to learn that hydrogen gas is fused, like literally glued together under immense gravity, to form heavier elements such as helium. And that process is known as nuclear fusion. And that process gives off a whole lot of light and other forms of energy. Okay? So a self-luminous, something that makes its own light, celestial body, is a star. A planet reflects light. It does not make its own light. Moons only reflect light. They don't make their own light. Okay? The reason why we see the moon at night is because it is reflecting sunlight. The moon does not give off its own light. Okay? And neither do the planets. All right, and then a light year. All right, number 7. 1 light year is about 9.5 trillion kilometers. Okay? Here's the number all written out. Here's the actual calculation for you to find that. Okay, if it travels 300,000 kilometers every second, and there's 60 seconds in a minute, and there's 60 minutes in an hour, and there's 24 hours in a day, and there's 365.25 days in a year, then that's how we wind up with that big number. 9.5 trillion is basically this number rounded off a little bit. Okay, so, but that's how I calculate that. That's how far light can travel in 1 year. And when I say light, I mean visible light, but I also mean other forms of electromagnetic radiation, like gamma rays, or X-rays, or infrared radiation, or ultraviolet, or radio waves, because those are all forms of electromagnetic radiation, just like visible light. And they all travel at the same speed, which is 300,000 kilometers per second. Okay? All right, so that should take you through the things that you need to add for Bell Work 2 of Unit 6. Make sure that you put this in your binder and use it as notes.